Hello, in this video we're going to talk about continuous functions and their relationship with integrability. Specifically, we're going to prove that continuous functions are integrable. Then we're going to use that fact and show that functions that are almost continuous are also integrable. And by almost continuous, I'm going to specify exactly what I mean. So first, any continuous function from a closed interval to R is integrable. Furthermore, the sequence of regular partitions of AB is an Archimedean sequence of partitions for F. Okay, so let's prove this one. What we need to do is we need to take the upper sum minus lower sum and show that the upper sum minus lower sum for some sequence, in fact they told us what sequence, the regular sequence of regular partitions approaches 0. Note that this function, because it is continuous, it is also bounded. So in fact we can talk about integrability. So let's start with upper sum minus lower sum and see whether we can show the fact that it would be it would approach 0 using the standard notation. We get upper sum minus lower sum is equal to the sum I equals 1 to n capital Mi minus lower mi times xi minus 1, where Pn is the sequence of regular partitions. Of AB. Okay, if you look at xi minus 1, since it is a regular partition, xi minus 1 is b minus a over n. Now, we have to show this guy is small. If you look at mi minus 1, we can take the largest of these and call it perhaps mj minus a lowercase mj. So suppose mj, so j is the one that gives you the largest of them, minus mj is equal to the maximum of this set, mi minus mi, I ranges from 1 to n. Note that since Pn is regular, xi minus 1 is just b minus a over n. Now if you look at the upper sum minus lower sum, that is less than or equal to, each one of the mi minus mi is less than or equal to mj minus mj, and xi minus 1 is b minus a over n. And there are n of these because there are n terms in the sum. So that's exactly mj minus lowercase mj times b minus a. Now, note that this mj minus mj, since the function f is continuous, capital MJ and lowercase mj are in fact functional values. So since f is continuous, by the extreme value theorem, there is some uj and some vj inside the interval xj minus 1 comma xj, such that f of uj is equal to supremum and f of vj is equal to infimum. Now take a look at this vj. So let me actually call this un and vn. because they do not really depend on j, they depend on n. So there are un and vn inside the interval xj minus 1 comma xj, that f of un is the supremum and f of vn is the infimum, because it attains its supremum and infimum, because it has a maximum value and it has a minimum value. So now we have to show that this quantity approaches 0. So the upper sum minus the lower sum is clearly greater than or equal to 0, less than or equal to f of un minus f of vn times b minus a. Now, note that un and vn, the distance between them is less than or equal to b minus a over n, since un and vn are in the interval xj minus 1 comma xj. So by the comparison lemma, limit of un minus vn is 0 as n approaches infinity. Okay, so I would like to show that f of un minus f of vn also approaches 0. So that reminds us of the uniform continuity. So note that since f from AB to R is continuous by the Heine-Cantor theorem, it is uniformly continuous. Therefore, the difference between f of un and f of vn also approaches 0 as n approaches infinity. So now if you look at this star, this approaches 0. This is a fixed number, this is a constant. Therefore, by comparison lemma, upper minus lower must also approach 0. So by comparison lemma applied to star, the limit of upper sum minus lower sum is 0, and therefore f is in fact integrable. Okay, so next, so this shows that every continuous function is in fact integrable. So next we're going to talk about functions that are almost continuous. They are not quite continuous. They are continuous everywhere except at the endpoint. So, and this idea can be actually extended. So if you have a function that is integrable and or at least almost integrable, then it would be integrable. So here is what I mean. Suppose f and g are bounded functions from the closed interval ab to r. F of x is equal to g of x for all x in the open interval ab. So the two functions are the same everywhere except for the endpoints. Maybe this function is like this, the other one is the same except at the endpoints that is like this, something like that. So if that is the case and one of them is integrable, then the other one would also be integrable. So suppose f and hence g is integrable over the closed interval CD for every closed interval inside the open interval AB. For example, when f is continuous over the open interval AB, then it would be continuous over every interval inside AB. And this is the one that we're going to be using almost exclusively. That's the only condition that we need. So this theorem is a bit stronger than what we usually would need. Then f and g are integrable over the closed interval AB, and their integrals are the same, which means The integral does not depend on the value of f at the endpoints. Okay, so the key here is we know our functions f and g are the same everywhere, and they differ at the endpoints. If that's the case, then their integrals are the same. Just changing the value at 1 point or 2 points, the endpoints, doesn't make a difference. Okay, so the idea is we're going to take the interval from a to b, and since we know that function f and g are integrable over every interval inside AB, we're going to take a sequence of intervals, maybe an comma bn, that approach a comma b. And then we're going to look at the upper sum and lower sum inside here, and we're going to show that this portion is bounded. This portion is actually like approaches 0. And therefore, the whole thing, the difference of the upper minus lower approaches 0. So let an and bn be two sequences such that a is less than an, less than bn, less than b, and an approaches a and bn approaches b. Now, since f is integrable on on a and bn, there is a partition Pn such that upper sum of f with respect to Pn minus upper sum of f, lower sum of f with respect to Pn is less than 1 over n. So we know that f is integrable. Therefore, upper sum minus lower sum approaches 0. Therefore, there is something that is less than 1 over n. Now consider this partition. Consider the partition, I will call that Qn, which is Pn, and then we're going to add a and b to this partition. Okay, so let's assume that I'm going to bound these portions here. Bounding these portions isn't that difficult. We need to know the height. So what is the largest value for f? So let's call that maybe some a. So since f is bounded, we have some upper bound. Suppose a in R satisfies f of x less than or equal to a for every x inside the closed interval ab. If you look at the upper sum of f with respect to Qn minus the lower sum of f with respect to Qn, we get the first piece is from a to an. So let's say sum m1 minus m1, and then a1 minus a. This is m1 and lowercase m1 are the, I'm going to write it down here. m1 is the supremum of f of x when x is inside a comma a1, and m1 is the infimum of f when x is inside an, inside bn a comma an. Then the portion from an to bn would be just the upper sum of Pn minus the lower sum for Pn. This is the portion that we know goes to 0, plus the portion at the end. I will call that m2, capital M2 minus lowercase m2, and that is b minus bn. m2 is the supremum of f of x, where x is inside the interval from Bn to B, and lowercase m2 is the infimum of the same set, f of x, where x is inside the interval Bn to B. Okay, so now what we know is that m1, m1, all of these m's, the m, capital M1, lowercase m1, capital M2, lowercase m2, are all at most a, because a was an upper bound for the absolute value of f. We know that m1, m2 in absolute values are all less than or equal to a. Thus, if you look at the upper sum for f minus the lower sum for f with respect to q, we get this portion. Let me point that this portion is at most 2a. This portion is also at most 2a. And this portion goes to 0. So it is 2a times an minus a plus upper sum minus lower sum. We know this one goes to 0 plus 2a times b minus bn. Since an minus a approaches 0, b minus bn approaches 0, and we know pn is a it also approaches 0, because I know that this one is less than or equal to 1 over n. I chose it in a way that it is less than 1 over n. By the comparison lemma, limit of upper sum for f with respect to qn minus lower sum for f with respect to qn as n approaches 0, infinity, is equal to 0. So now that implies that thus f is integrable on AB. And of course, the argument for G is exactly the same thing. Furthermore, integral from a to b of f is the limit of the upper sum of f with respect to qn, because we showed that qn is in fact a we showed that qn is in fact an Archimedean sequence of partitions. However, if you look at the upper sums, we know what the upper sum is. Upper sum is capital M1 times an minus a plus upper sum f with respect to Pn minus lower sum f with respect to Pn plus capital M2 b minus Bn. Okay, so note that an approaches a and m1 an minus a is less than or equal to an minus a. Thus, m1 times an minus a approaches 0 by the comparison lemma. And then similarly, m2 times b minus bn also approaches 0. Therefore, what we get is this. Integral from a to b of f is the same as, oh, I'm sorry, I don't actually have that minus sign here, is the same as limit as n approaches infinity of the upper sum of f with respect to Pn. But, however, upper sum of f with respect to Pn does not depend on f of a or f of b. In other words, upper sum of f and upper sum of g are the same. Thus, integral of f and integral of g are the same. So if you have two functions, the value at the endpoint doesn't really matter. As long as they are the same inside the interval and they are integrable inside the interval, they would be integrable over the whole interval, and the integrals would be the same. You do need the functions to be bounded. Okay, so that's good. So we can now expand our understanding of integrable functions. So we know all continuous functions are integrable. All monotone functions are integrable. All step functions are integrable. Now we also know functions that are almost continuous are also integrable. You just take some integrable function or some continuous function and just manipulate the endpoints. Okay, so here's an example on this topic. If you look at this function from closed interval 0 to 1, 0, 1 to r, and the function is defined by 1 when x is 0, sine of 1 over x times x minus 1 when x is between 0 and 1, and 2 when x is 1. Then we want to show that f is integrable. So note that f of x is less than or equal to 2 for every x. Thus, f is in fact bounded. So that's the first thing. Also note that the function is continuous over the open interval. Also, 1 over x times x minus 1 is continuous on 0, 1. And thus, if you compose it with sine, f is continuous on the closed interval 0, 1. So by the previous theorem, by theorem the one that we just proved, 7.9, f is integrable. Because it is bounded and it is integrable inside the interval. And in fact, the value of the integral doesn't depend on these two, this one and this one. For all we know, we could change this one to 1000 and change this one to pi, and we would still get the same integral. And the reason is clear, because if you have graph of a function, changing one point doesn't change the area. So the one point doesn't give you any new region. Okay. So finally, we will do one more example on this, and that would be the last thing we're going to do today. Prove that the following function is integrable on 0, 2, and evaluate the integral from 0 to 2. Okay, so first of all, this function is bounded. F of x is bounded by 3. The largest value of this is 1, the largest value of this is 2, the largest value of this is just 3, and the smallest values are just 0. So f is bounded. Also, f is continuous on the interval 0, 1 and 1, 2. Thus, f is integrable on both intervals 0, 1 Thus, f is integrable on 0, 1 and on 1, 2. Also, the integral for f is the same as the integral of x dx. This one we have actually done it before. This is 1/2. An example. Integral from 1 to 2 of f is integral of x minus 1 dx from 1 to 2. Because again, it's integrable and it is the same as x minus 1. The endpoints do not matter. Now, by linearity, I can break it up into integral from 1 to 2 of x minus integral from 1 to 2 of 1, both of which we know what they are. This one is 3/2, so that's an exercise we have done, minus, and this one is 1, so this is 1/2. Now, since f is integrable on 0, 1 and on 1, 2 by an exercise, f is integrable over the interval 0 to 2, and by additivity we could now say the integral from 0 to 2 is the same as the integral from 0 to 1 plus the integral from 1 to 2. And each one of these we evaluated. That brings me to the end of this video. Okay, so if you would like to continue with this topic, feel free to subscribe. And I will see you in the next video.